Okay, this is section 2.4, and my next slide will have that on it. But let's talk about what we have in our tool belt so far. Okay, we know the derivative of a constant. We know the power rule. We have the derivatives of our 6 trig functions. We have quotient rule, and we have power rule. Product rule is what I meant to say. I already said power rule. Okay. If you can do all of those in their very basic sense, then we should be able to apply them to other things. Okay. Now, there are some problems that we wouldn't be able to take care of with just those right there. Okay. So today we're going to talk about what if we have a lot more going on than just like a product and a quotient or putting those together. Okay. The chain rule is going to help us with composite functions. Before I move to my first slide, what is a composite function?
So like f of g of x.
Yes. F of g of x. We have a function inside of a function. Okay, and that's what the chain rule is going to help us with today. Okay. So the chain rule, this is what I would write down. The chain rule uses the idea of composite functions. Okay? You don't need the rest of that up there. Okay? We're still going to use the rules that we've used so far, like power rule, product rule, quotient rule, and trig derivatives, inside of the chain rule. Okay? So the chain rule is a process where we still need our other rules from before. Okay? So when I move to the next slide, it's going to have the rule. I'm going to circle, you're going to box, whatever, in your notes. Write it down first, and then I'll explain what it means. Okay, I don't want to try to write, or I don't want you to try to write as I'm explaining. So, if f is differentiable, g is differentiable, and we have our composite, blah, 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 blah. This is what I want you to write down. Okay? The chain rule. Write big. The chain rule. And write this down. So notice how I even have the explanation up there for you, okay? But anytime we have a function inside of a function, okay, we are going to take the derivative of the outside function, whatever that may be, while leaving the inside alone. Then whatever's on the inside, we take that and multiply by its derivative. Okay, we are going to go through a lot of examples today where you can see what that process looks like. Okay, but anytime we have a chain rule problem, I'm going to use that description. Derivative of the outside, leave the inside alone, times the derivative of the outside. And I hope that you kind of tell yourself that as you're doing the problem. Okay, But the biggest thing to look for, okay, since we're talking about a composite function, do you have a function inside of a function? Okay, if you don't, the chain rule is not necessary. Okay, and we can use one of our other basic rules. So let's go ahead and write this first example down. Okay, well, since this is cosine, whatever's inside of cosine has to stay in there. Like x squared plus 9 is like the angle inside of cosine, so there's no algebraic way for us to break that apart. Does that make sense? Okay. If we were given, and like we'll talk about something like this, okay, you have the option of we could use the chain rule or we can multiply that out into a different rule. Okay. So you have some options in some cases. Does that make sense? Okay. All right, but this would be an instance where we don't have the option. X squared plus 9 has to stay inside of cosine. There's not an algebraic way for us to break that apart. Okay? So our outer function is cosine. Inside of cosine is x squared plus 9. Okay? So when we take the derivative, we take the derivative of the outside. What's the derivative of cosine? Negative sign. So we have negative sign, and our inside stays the same, times the derivative of what's inside. Well, inside is x squared plus 9. The derivative of x squared plus 9 is 2x. If it were me, I would go ahead and rewrite this as negative 2x sine of x squared plus 9. I would rewrite it just to make it look a little bit nicer, but it's the same either way. What do you think? Okay, so just do lots of examples. No? Write this down, and as a pod, talk about what you think the derivative is.
Oh yeah, 2 times.
Yeah.
Nothing else.
Oh, you're ready. Okay.
All right. Mandy, talk me through what you did.
Well, we took the derivative of the outside first,
Which is?
cosine,
Okay.
and then we kept the inside the same. And then you multiply that by the derivative of the inside, which is 2.
Okay. Caleb, do you agree with cosine of 2x
Yes.
times 2?
Yes.
Perfect. I would probably rewrite it as this. Just because it looks pretty good. Yeah. Do you have a question?
No.
You're just saying woohoo? Yeah. Okay. Let's step it up.
Oh. Oh.
I'm sure you've been very curious about a problem like this. Okay. Fine. Okay. So we did a lot of rewriting when we used the power rule. We cannot use the power rule here because we can't split a radical up if there's addition or subtraction underneath. Okay. However, we can rewrite this to 5 minus 3x to the 1/2 so that when we apply the chain rule, we can do so using the power rule. Okay? So inside function 5 minus 3x, outside function we're being raised to the 1/2 power. You see that? Okay. So now when we take our derivative, our outside function is that 1/2 power. Well, power rule tells us drop the power and decrease it by 1. Chain rule says you better keep that inside the same. And then multiply by its derivative. What's the derivative of that inside? -3. Okay, so you could write -3/2 times 5 minus 3/2, 3x to the -1/2. Okay, I don't need any big fancy rewriting. Okay.
I'm
Yes.
still confused a little bit about like the outside function. Like how did you get
Like, how did I rewrite it up here? Or how did I decide that the 1/2 power was my outside function?
yeah, how did you know that it was an outside function?
Okay. Well, since 5 minus 3x is underneath the radical, okay, I would say that that's the inside function. And since it's inside the radical, then that radical would be the outer, right? And so when we write it to that 1/2 power, we now have that as our outer function.
So like the outer function was like radical x and then like g of x was 5 minus 3x.
Yes.
Okay.
Yes. Okay. You're gonna see, and like I said, I'll have an answer key for you to look at again with my work tonight. The book is gonna rewrite this to where you have that radical down in the denominator. I don't need that. Leave it like this. Okay. All right. You had a question on your quiz. When was your quiz? Was it Wednesday? Right? Yeah. You had a question on your quiz Wednesday. That was this. You remember that one?
Yeah.
Colby, tell me what you did for that one.
I just won't put it out.
You multiplied it out, and then we could use the power rule, right? Okay. Which was your only option on Wednesday. And it would still be a fine option, but you now have a second option because we can apply the chain rule to this composition function. Okay, chain rule. We have 2x plus 4 inside of a squared, right? So what we can do is we can apply the power rule. Keeping our inside the same, and then multiply by the derivative of the inside. So we get 4 times the quantity, 2x plus 4, which is being raised to the first power, which is the same thing as 8x plus 16. And I remember that that was the answer. Some of you might remember that also.
Would you want us to leave it like that and multiply it down? It's not.
I'm fine with you leaving it like this. Okay. Now, when we get to unit 3 and we have to use this to like set it equal to 0, then you're going to have to do some algebra no matter what. But I'm fine with this. Okay. All right, I'm changing my mind on the example I want to do, so just ignore that. The example I want to do is this one. Okay. Don't do anything yet, but what I want you to talk about at your pod, A, is this a composition function? And B, if it is, what's inside, what's outside? Okay, go.
We know that triggers.
Maybe there's a trigger. But then we don't like this shit. But then we have to like.
That'd be like the cosine of the thing in the parentheses. For example, my cosine is x from the side. Yeah.
So you have to calculate that extra. That's weird.
All right, Eli, I'm going to ask you to speak for your group.
I was getting a math book from Robert Price. So
Okay.
I'd be responsible.
What's my cell phone? Okay, but I still want you to talk for your group. Okay, is this a composition function?
No.
Why not?
Because it's a product.
You are viewing this as a product. Okay. How many of the other groups view this as a product? Okay, Colby, you made this big gesture. What do you view it as? What would you talk about? Well, what did Pod 1 talk about?
We weren't really sure.
That's what you talked about. I don't know.
Half of us said yes, half of us said no.
Okay, so the half that said yes. Okay. What's the inside function? What's the outside function?
Outside would be 2. And
Okay.
then the inside would be tangent.
Okay. If we view this as a composition function, which we can, tangent is inside of the square. Like you could even say this is tangent of x squared, right? And Eli, I'm going to come back to your group's discussion. Okay. If that's the case, then we take care of that power rule first. And then multiply by the derivative of the inside, which is tangent. Okay. What's beautiful about math, especially what we're doing right now in our derivatives unit, there are a couple different ways we could approach a problem. Eli, I want to revisit your product. Okay? Are you 6? Pod 6 was viewing this as a product rule. Okay? So if we are thinking of this as tangent times tangent, so you're thinking tangent times tangent, then we have the derivative of tangent times the second function, maybe I should say that, plus the first function times the derivative of the second function. Hey, guess what? Do we get the same thing? We get the same thing. We have 2 terms that are tangent of x times secant squared of x. We get the same thing. Now, where you may run into trouble, Eli, is if I would have given you tangent to the 4th x. Then the product rule probably wouldn't have been very much fun for that one. Okay, the chain rule would have been a lot more efficient. Okay, but it's nice that we have options, right? Okay. Another opportunity where we have options. How many of you think, man, I should do the quotient rule here? That's like our instinct right now, right? It's a fraction. I should use the quotient rule. Guess what? You do not have to use the quotient rule for this problem. How so? Could you rewrite this as 3x minus 2 to the negative 1 power. Okay, the quotient rule, is it messy? The quotient rule is messy. Watch this. Our derivative. I have now written it as a composition. Thank you. We can now take the derivative of the outside. We have a power rule. Okay. Times the derivative of the inside. So what we have is negative 3 over 3x minus 2 the quantity squared, which is exactly what you would get if you were to use the quotient rule, but it would take you a lot longer to get there. Okay, bless you. There's nothing wrong with using the quotient rule, but now you also have the option of using chain rule. Yes?
Could we just keep it as, like, instead of putting it back in the bottom, could we just keep it as negative 2?
Yes, if you keep it as negative 3 times 3x minus 2 to the negative second, I am perfectly happy with that. Yes. Oh, look at that. I had all those ready. Forgot I did that. All right. Write this one down. No?
Is this one where we
Is this where we have to what?
obviously like do more than one rule? Yeah.
Well, in all of these, we've been doing more than one rule. Like the chain rule requires you to use the other rules that we know. Does that make sense?
What's the second one?
Okay. Do we have a composition function? We have a quotient inside of the 7th power. Okay. So let's take care of our outside function first. That's the easy one, right? Our outside function. Drop the power. Drop the power by 1. Times. So derivative of the outside, leave the inside alone, times the derivative of the inside. Why did I make such a big parentheses? Our inside is a quotient rule. Okay. Oh, that's one of like the least intimidating quotient rules I could give you. Okay. There is linear divided by linear, okay? We've got this. So derivative of the numerator?
2x. 2.
Times the denominator minus numerator times the derivative of the denominator. I was going to give you a chance. All over, oh, that's not the denominator. All over the denominator squared.
Can we leave it like that?
To be honest, I'm perfectly happy with you getting to here. Okay? Okay? But let me just show you what we could do, okay? Let me show you what we could do. This would be 6x plus 10 minus the quantity 6x minus 3. So we get 10 minus negative 3, which is 13, and the 6x's cancel out. You're just sitting back and watching, okay? So this is, if I were to ask you to simplify this all the way down, you would do that, and then watch. This is like 3x plus 5 to the 6th power in the denominator. So what we could do, and you're not going to do this, is we could say, okay, well, if we make this one big fraction, I could write, well, 3x plus 5 is to the 6th here, to the 2nd here, is to the 8th power. 7 times 13 is 91, and 2x minus 1 is to the 6th power. Okay? But that is not necessary. All that is algebra, people, but it's not. We don't need to do it. You do it. Okay, I'm going to let you vote on our last example. I have 2, I only want to do 1. Okay? Don't make any noises, just think. Option number 1 or option number 2. Who votes for option number 1? Who votes for option number 2? Barely, but we're going to do this one. Okay, individually, I know that you can apply these rules. The chain rule makes you apply multiple things together, so you really have to keep your head squared away. Okay, guess what? Tomorrow, I'm not teaching you anything new. We're just doing more complicated examples of the chain rule. Okay, so like this is the last thing that you're learning new before Thursday's quiz. All right, we have a lot of time to practice. Okay. All right, so first of all, do we have a composition? Yes. Okay. What's our outside function? The negative 8th power. All right, so let's take care of that first. Drop the power. Leave the inside alone. Ooh, what's our new power? Tempting to write -7, isn't it? Okay. Times. Now we have to take the derivative of the inside. All right, what's the derivative of 1? 0. Perfect. Plus x to the 5th times cotangent of x. What do we need to use? The product rule. So the derivative of the first function times the second plus the first function times the derivative of cotangent would be what? Adrian, you're looking it up. Negative cosecant squared. My suggestion, just because everything is pretty intense, I would rewrite this as 5x to the 4th cotangent of x minus x to the 5th cosecant squared. That way it just looks a little bit nicer. Okay. I also want you to think about those two are multiplying, so we have a negative term right there. Okay, but that's our derivative. And you can stop right there. Not on this. Once we get into unit 3, you're not going to have a choice of stopping because you're going to have to get all the algebra worked out. Okay. All right, so let's talk about our homework quick. Your homework is actually not very long. Total, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 problems, but that's like total. That's like not like, that's bolded and unbolded combined, and I fit all of mine on one piece of paper, and I don't write that small. So, it's not super intense, but we have to practice. Okay? Power rule, we can do individually. Product rule, we can do individually. Quotient rule, we can do individually. The chain rule makes us kind of combine everything together, so we really, really need to practice. Okay? I cannot tell you enough. You just have to practice. Okay? If after the homework is done and you're like, man, I really need more practice, feel free to pick problems that I didn't assign you. Okay? You're always welcome to do that. Okay? Just for your planning purposes, okay, tomorrow we'll do more examples.